Good afternoon, ladies and gentlemen. Welcome to the I²CNER seminar. I'm Takata from Thermal Science and Engineering Division of the I²CNER. Today we have a speaker from KTH Royal Institute of Technology, Stockholm, Sweden. So, first of all, I'd like to introduce Professor Luca Brandt. So, he is a professor in fluid mechanics at KTH Stockholm, and he obtained his PhD in 2003, and since 2012, so he became is serving as a professor at KTH. So he has been working on the transition of turbulence, flow control, biofluids, complex fluids, and multi-phase flows. And he recently established the new research center and serving as a director. So that is a multidisciplinary research center interface, which is supported by Swedish Research Council. And he is serving as an associate editor of Mechanica and the European Journal of Mechanics, Fluids, and in the advisor board of the International Journal of Multi-Phase Flow and flow, turbulence, and combustion. So today's his topic is numerical simulations of turbulent flows of particle suspensions. So please start, Professor.
Okay, thank you very much. Thank you for inviting me here. You can hear. And it's, I thank Professor Takata for the invitation. As you mentioned, we recently started a new center where we plan to study in particular wetting and boiling, phase change, heat transfer and phase change. So I'm here also to learn about all these nice experiments and activities we have here in Japan. But during my talk, I will present what I've been doing the last, say, 4 or 5 years. It's about particle suspensions, so suspensions of rigid particles, and most of the work, and say all of the work that we present here is based on large-scale numerical simulations. If this microphone is okay. So let's start. So first, I start acknowledging many collaborators. We can start with, for example, Pedro Costa and Wilhelm Bregen from Delft in the Netherlands, contributed to the development of the numerical code. Then we have Francesco Picano, who was postdoc at KTH and now moved to Italy, University of Padua. Then I listed here some of the students at KTH who were involved in this project, but also Dr. Mitra from Nordita, which is the Nordic Institute for Theoretical Physics that is in Stockholm. So as we start, so what we want to study suspension of rigid particles, and these are found in many natural phenomena, for example, the pyroclastic flow, sediment transport, and many other applications that you see here. And of course, these flow with particles are very important in industry. And one can mention that about 10% of the world energy consumption is used to transport solid materials through fluids. So what we want to do is understand the transport of the mixing in these suspensions that we find in many industries, fluidized beds. That's something that I will shortly mention also later on, but also waste slurries, for example. So if let's see if this microphone works. If we focus more on the scientific point of view, what is the scientific challenge here? Okay. Is it on? Hello? So I was mentioning that, as we said, suspensions are everywhere. You can find them in several different fields. And from a scientific point of view, the motivation is to consider dense suspensions and to concede finite inertia. So what I mean with dense suspensions, I mean that the distance between the particle is of the order of the particle size, so that we have to consider all possible interactions, collisions, short-range interactions, hydrodynamic mediated interactions, all contribute to the dynamics of the suspension. At the same time, we will not study strictly the rheology of the suspensions, but we will assume the flow happening at finite inertia, basically in practice finite Reynolds number, and because that's the most common case that you have in industry and in many applications. So we will consider basically the flow to become turbulent, not only in a simple laminar flows. So this is more or less the outline of the talk. First, I will talk about the numerical tools, how we want to study these numerical particle suspensions, and then I will talk about flow in channel flows, and the role of turbulence, and then at the end, I will include additional effects that we are modeling, and that's the particles, different shapes, heat transfer in the suspensions, and so on. So as I said, most of this work is based on large-scale numerical simulations. So this requires typically from 1,000 to 4,000 cores for one case, some of the cases I will show here. But so we have to develop these efficient and accurate algorithms that can run on these large supercomputers. But when it comes to multi-phase flow, it's always a question if one is doing real direct numerical simulation, or if there are models in the simulations. And also in our case, of course, we will have to model the interaction between spheres and solid walls, or collision between spheres. So what we're going to solve, basically what we solve is a Navier-Stokes equation for a fluid, here written for an incompressible fluid. Typically, we will consider particles are naturally buoyant or slightly heavier than the fluid. So let's say this is typical equation for water. Navier-Stokes equation, which is governed by this Reynolds number. So, and then we solve the Newton-Euler equation for spherical particles, or for particles of different shapes. That's basically an equation for the linear and angular velocity of the particles in the flow. What the problem is that, of course, is what is called the curse of the boundary conditions. Basically, what we have to do, we have to impose a boundary condition, which in this case, in most of the cases, will be no slip and no penetration at the surface of these particles. And these particles are of the order of 50,000, 100,000, and they move in the channels and the pipes. That means that we need to impose boundary condition on moving surfaces. And this, for the first part of the talk, will be this no penetration of the fluid into the solid particles. But as I will mention very short at the end, we are now looking at evaporating droplets for fuel sprays, for example. And then we will have boundary condition also on the heat and mass transfer across this interface. But for the first part, we will talk mainly about these rigid particles and how we model the boundary conditions. And this is done by what is called the immersed boundary method. Basically, the method reduces to solving questions on two different grids. We have this red mesh is basically an Eulerian grid. We mesh our domain, could be a channel, a pipe, and then we solve the equation for the fluid phase, an Navier-Stokes equation on this regular Cartesian mesh, and this could be done in an efficient way because it's a very standard approach. But then when it comes to the solid body, we basically assume a set of uniform Lagrangian points attached on the surface of the particles, in this case of a sphere. So we have these black dots which represent a mesh on the surface of the particles, and they are more or less equally distributed. And what we do is we basically exchange information between the Cartesian mesh, the Eulerian mesh for the fluid, and the Lagrangian mesh for the rigid particles by doing interpolation and extrapolation. And we force the velocity basically on the rigid particle to be zero, so that there is no relative velocity in the fluid and the particle. So in this way, we don't need to follow the particle, but we can keep the same background mesh and just add an additional forcing term here into the equation for the fluid. And this additional forcing term is basically mimicking the presence of the particle. Of course, this requires additional computational costs, but not as much as remeshing and following different particles. Of course, this will require sufficient resolution, and typically what we have is that to well resolve one particle, we need that the diameter of the particle is at least 24 grid cells. So we need to resolve the particle diameter with at least 24 of these cells. Now, this is an equation for this is how we solve it for the particles immersed in a fluid, but what we want to do is that, of course, at some point we need some models for interaction between spheres with each other or spheres at the solid wall. So the thing is that because we use a fixed grid, at some point if the particle will come too close to the wall, then we will not be able to fully resolve the fluid in between the particle and the wall. We will not have enough resolution. And at this point, we will have to model these interactions. Basically what we have, we implement some corrections which are based on analytical solutions for interaction between two spheres or a sphere and the wall, and they are added as correction to the lubrication force between the sphere and the wall. Of course, we need a certain threshold below which we activate this correction. So that's the first correction we do, is we estimate better the lubrication force, the force that is due to the thin layer of film between the particle and the wall. The problem is that this analytical solution are becoming infinite as the gap width goes to 0. So at some point we cannot let this distance go to 0, so we will introduce a roughness correction, so that when the distance between the particle and the wall is of the order epsilon 1 here, where this is typically of the order 1% of the particle radius, so it's something relatively small, then we cut the lubrication force and we assume that there is some kind of finite lubrication force due to the presence of roughness. But at the end, eventually, we will have that, since we are considering turbulent flows and inertial flows, there will be a collision between the particle and the solid wall. And in this case, we will adopt some collision model. In this case, what we do is we use the soft sphere collision model. And the characteristic of this model is that it can allow a little penetration of the particle into the wall, but that's still of the order of 1–2% of the particle radius. And this is done actually because we don't want to pay too much in terms of time step. Because if we can have a more rigid collision, then we will have to decrease the time step. Allowing the particle to penetrate a little bit into the wall will enable us to have a longer time step, so the simulation will be more reasonable. Okay, so this is the method. Basically, we have the particles immersed in the fluid, and we have each particle associated with a Lagrangian mesh, and we track the particles into the fluid, and then we exchange forces between the fluid and the particle. So the forces from the particle on the fluid will be added on the Navier-Stokes equation. The forces from the fluid to the particle will then be integrated to estimate the force and torque acting on the particle, so that we can then update the particle position. Of course, when two particles come too close to each other, then we will have to take care of it, and this we do by this collision model. First lubrication, then collision model. So let's go now to the results. I want to first talk about the different flow regimes in channel flows. Because this was already an open question when we started this, 2012, 2013. So we want to know what kind of flow we have in a channel or in a pipe when we have many relatively large particles. So we consider particles which are relatively large compared to the pipe diameter, as in many applications, as in, for example, we have a project with Tetra Pak we'll mention later, where they're interested in transport of particles which are relatively large as well. And so the question is, what type of flow do we have? So first we want to refer to these experiments by Matas, Guazzell, and Morris, published in 2003 in Physical Review Letters, where they look at naturally buoyant finite-size particles in pipe, and they look at the spectrum of the pressure drop between the entrance and the exit, and to determine whether the flow is laminar or turbulent. And so this is the results. This is basically the Reynolds number, so it's a kind of non-dimensional inertia, so that Reynolds number are inertial forces, this is proportional to the flow rate. And then we have the result, and this is the phi, the particle volume fraction, so the percentage of the volume which is relative to the solid phase. So it will be 30% particles in a unit volume of fluid and particles. So what we see is that basically there is a non-monotonic behavior for relatively large particles. The critical Reynolds number for the onset of turbulence first decreases, so it's easier to have turbulence, and then increases. So that when you have many particles, then the flow seems to stay laminar for a longer period of time, which we'll show later is not really the case somehow. These were experiments, so what they did also is they say, okay, since we have particles in the flow, in water, what we do, we consider an effective viscosity of the suspension, which is basically the viscosity which is enhanced due to the presence of the particles, as in classical rheology studies. So you have an increased viscosity due to the presence of the particles, and by doing that, they see that if the particles are relatively small, about 1/50, 1/60 of the diameter, then they see that the critical Reynolds number is more or less constant. But for larger particles, we observe again a decrease on the critical Reynolds number and then a kind of a plateau. So they mentioned that, okay, it's not clear when you have relatively large particles what's happening in the flow. It seems there is some additional dissipative mechanism. More or less at the same time, as we started this work, was a group in China, I think Tsinghua University, that performed simulations that was with a method similar to ours, similar to the simulation trying to reproduce the experiments. And this is for one case, of course, the simulations are very expensive. You cannot do really as many cases in experiments. But what they did, they choose one case. This is the Reynolds number, and this is the volume fraction. You see the experiments are the symbols, these are the simulation, and they more or less reproduce the trend. At first, the critical Reynolds number, the onset of turbulence is earlier, but then as we increase the number of particles, the onset of turbulence is delayed. But when doing that, these authors also noticed that they had somehow to find a way to define if the flow is turbulent or laminar. And they used as an indicator the kinetic energy of the perturbation, and they selected a certain threshold. But they write in the paper that, okay, we select this threshold such a way that we can get qualitatively good results, so qualitatively reproduce the value of the critical energy. But of course, this threshold changing this threshold value will also change the results. So again, there is something that was not clear. So more or less at that time, we also did simulations of channel flow. Okay, these are the simulations. Now, this is not a pipe, as in the experiment, it's a square channel, but physically it's the same. We see that we show the same trends. And we investigate a range of Reynolds number from 500, where the flow is supposed to be laminar and smooth, to 5,000. And then we have a lot of volume fraction from 0.001, that basically means 4 or 5 particles inside the computational domain, up to 30%. And the particle radius is about 1/10 of the half channel width, which is exactly as one of the experimental data sets. So now, first I want to show you what happens in the flow if we look at the velocity, the fluctuations in time of the flow. Basically, this is the kinetic energy of the streamwise velocity fluctuations. So we see that this is 0.001%, is really like, I think, 5 or 10 particles in the whole channel. And then we see that red colors is low Reynolds number, and then there's more purple-like is higher Reynolds number. We see that we excite the flow, we disturb the flow, and then as we wait some time, if the Reynolds number is low, the flow will be a little bit chaotic, and then the perturbation will decay, so that eventually we will get back to some kind of laminar smooth flow. But if we have a higher Reynolds number larger than 2,000, then we see that the flow will go turbulent, and then we will have sustained oscillation fluctuations in the flow. If we have 5% particle volume fraction, then we see that now in the presence of particles, we still can distinguish two regimes. If low Reynolds number, there is the flow sets to some level of fluctuations. Because of the particles transporting the flow, there is no more simple laminar flow, but there are anyway fluctuations, and there is some chaotic motions due to the presence of these many particles. But if the Reynolds number is large enough, we see that the oscillation will settle to a level which is similar to the case with few particles, and this is more or less, this is the somehow classic turbulent flow. But then if we increase even more the volume fraction, more than 20%, this is for 30%, we see that now at 30% volume fraction, we transport particles, but the level of fluctuations in the flow is almost independent of the Reynolds number. Now, Reynolds number 500, Reynolds number 5000, there is a difference between 5% to 7% in the level of fluctuations, but we see that this fluctuation is almost constant in time, and in this case, it's almost impossible to distinguish between some kind of smooth laminar flow, like here, and a more chaotic turbulent flow. So that's what the point that also was made by the other group doing simulation, that, well, they choose a threshold value to define laminar turbulent flow, but they didn't know basically exactly what was the best choice. So what we do now, we try to analyze this flow, and we go back to some decomposition, some kind of theoretical approach, which is actually due to Prosperetti and co-workers, study from 99. So what we do, we take the equation for the momentum equation for and we average on the fluid and particle phase. We do a phase ensemble average, so that we can write a momentum balance equation for a fluid phase and particle phase, where we have the contribution for the particles phase, for example here. Now, because this is the general form of the momentum equation, considering all possible terms, but then because we have a channel flow is a relatively simple geometry, because we have that everything is homogeneous in the streamwise direction, so there is no variation along the flow. It is a steady state, everything is symmetrical in the spanwise direction, this is an infinite wide channel. So all the main quantities will only vary across the channel, so in the wall normal direction, from one wall to the other one. So if you do this symmetry, then one can integrate, and then can write that the total stress in the channel, which is basically proportional to the imposed pressure gradient to drive the flow. So the imposed pressure gradient is balanced by these three contributions, where the first one is the viscous stress, viscosity times 1 minus phi, because viscosity acts in the fluid phase, the du dy, which is basically the gradient of the velocity. So basically this is a viscous stress. This is the Reynolds stresses. These are the turbulent Reynolds stresses. They are responsible for mixing and turbulent flows, transport and turbulent flows. And these Reynolds stresses actually have a contribution from the fluid phase and also a contribution from the particle phase. So this is basically this classical term that you want to model in turbulence. And then you have a third term, which is due to the presence of the particle. And this consists of all transport of momentum due to particles. And this is the so-called stressless, so the fact that the particle is actually solid, it cannot deform. But it also contains all terms relative to collision between particles and collision with the walls. So now we have these three terms that contribute to the transport of momentum in the case of a turbulent flow. So now let's see what happens. Then if you look at the momentum balance, at the transport in the flow, in this for all the simulation we perform, basically we could identify three different scenarios. First one is where Reynolds number is low and the particle volume fraction is not too high, 5%, so relatively few particles and low Reynolds number. In this case, what we see, this is not the total momentum transport across the channel, but this is the wall, this is the center of the channel. We see that almost all of the momentum transfer across the channel is due to viscous stresses. And then we have a little bit for the particle stresses, which is the green. And this is what typically happens when you have a laminar flow. Laminar flow is dominated by viscous forces, and that's exactly what happens in this case. Of course, you also have some contribution from the particles, but it's mainly viscous. If you now go at high Reynolds number, 5000, and volume fraction of 10%, then we see the transport is now dominated by this red contribution, which is the Reynolds stresses, which as in classical single-phase turbulence. So then everything is dominated by the Reynolds stresses, so by the vortices and the structure of the turbulent flow, except close to the wall. In fact, close to the wall, we see that viscous stresses dominate. But that's a classical thing in turbulence. You have this viscous sublayer, so that you have that, And then you have so that viscous force becomes relevant close to the wall, where the velocity fluctuation goes to 0. And then you have a contribution also for the particles. And then you have a third region, which is a relatively high volume fraction, an intermediate Reynolds number. That was the case where it was difficult to distinguish with the laminar turbulent flow. Then we see that in this case, all the momentum transfer, so the transfer momentum or the balancing of the pressure gradient driving the flow, is due to the particle stress. So now the particles that are responsible for dissipating, basically, because this is similar if you look at the energy instead of momentum, basically the particles are responsible for dissipating the energy which is needed to drive the flow. So we have seen we have three different scenarios. So what we could do, what we did, we should basically look at a map in Reynolds number and particle volume fraction, where we could identify these three regions. So F, low Reynolds number and low volume fraction, we have a region where viscous stresses dominate. So viscous forces are the most important. Now you have a laminar flow. If you now keep low volume fraction and increase the Reynolds number, then you transition to what is more or less like a classic turbulent flow, where the Reynolds stresses dominate the dissipation. And then we have here at high volume fraction a region where particle stresses are the most important. And that's something that we call inertial shear thickening. I will say a little bit more. Here is all the green is where the major integrated contribution comes from the particle stresses. And the black lines here are where each contribution is actually more than 50% of the total budget. So here it means that more than 50% go particle stress, here more than 50%. And here in between, one of the three dominates, but maybe less clearly. So this is to say that in practice, we always have these three contributions: viscous forces, particle forces, and classical Reynolds stresses, turbulent mixing. But so there is no really sharp transition, but of course in each region one of them will dominate. It's not that the other one disappears. So what is this idea of inertial shear thickening? What happens basically in this region where the transport and the dissipation in the flow is dominated by the presence of the particles? In this case, we have an increase of the dissipation, so let's say of the relative viscosity, with the shear rate, at fixed volume fraction, with an increase of Reynolds number. So we increase the speed, we increase the dissipation, but this is not associated to an increase of the turbulence. So basically we have an increased dissipation, but not a transition to turbulent flow. So to explain this, we look at the total contribution to dissipation due to the different forces we have seen before. Now instead of looking at the map, basically we look along a line. If this is very low volume fraction, 2.5%, this is Reynolds number, this is a different contribution. We see that basically when Reynolds gets about 1,500, we switch from a regime dominated by viscosity to another regime which is dominated by the red, which is the turbulent stresses. So there is somehow a really sharp point where you go from a laminar flow, viscous dominated, to a turbulent flow where turbulent stresses are the most important. If you now do the same at 30% volume fraction, then you see that the total dissipation, which is black, is basically following the green, which is a contribution for the particles. So no matter what the Reynolds number is, we see that the particles are always the largest contribution to the total dissipation. Of course, there is a little bit of increase of turbulence with the Reynolds number, but still this stays well below the contribution from the particles. So this is then what we call inertial shear thickening. We increase the Reynolds number, we increase the velocity, and we have an increase of dissipation due to the particle stresses. So there is not an increase in dissipation due to Reynolds stresses. I mean, they contribute, but the main part comes anyway from the particle stresses. So if I want to summarize what we have seen that if you transport particles, relatively large particles, in a channel or in a pipe, you can identify three different regimes of transport: a laminar flow, turbulent flow, and a regime dominated by the presence of the particles. They are not really sharp, there is not really a sharp transition between one and the other. Basically, all these mechanisms are important and present, but it depends on different conditions, which one is the most important. So we have seen that we have a region dominated by viscous forces, where Reynolds number is low, inertia is not so important, and particle volume fraction is not so high, so we don't have so many particles. If you increase Reynolds number, then you get a turbulent regime, like particle-laden turbulence. We have an increased dissipation and mixing due to Reynolds stresses. So in this case, you can retrieve the classical structures of a turbulent flow. I will show now some visualization. But then you also have this third regime, which is dominated by the presence of the particles, which we call as a continuous inertial shear thickening. So the presence of increasing in speed, so increasing in inertia. We have an increase in dissipation in the flow without clear transition to turbulence, without really the appearance of a turbulent flows. Okay, now I want to talk a little bit more about turbulence. I want to first say something more in general about the assumptions we did. Basically, now I want to talk a little bit about this region here, where the flow is turbulent, but of course the particles are present. Particles do not dominate, but they are relevant there. So one thing that I want to say is that, of course, what are the limitations of these simulations? Because, of course, this is a classical simulation. This is a turbulent channel flow with these particles. Now, particles are everywhere. Just in this visualization, we just cut them to show a little bit the flow structures. But the idea is that, of course, we have particles now that are 1/20 of the channel gap. So basically, we can align 20 particles from one wall to the other. But so what does it mean? And this is a little bit a limited set by computational resources to some extent. So the question is more or less, what does it mean? What are we doing here, right? And what is that we miss because of computational resources that, of course, are limited? So if you take one example of transport of sediment, for example, or industrial processing, typically you have pipe diameters that can go up to 1 meter, so speeds that can go up to 10 meters per second. Reynolds numbers are huge. Reynolds number is basically based on the pipe diameter and the flow in the pipe. It can be 10 to the 7. If you can then build the Reynolds number based on the friction of the wall, as typically done in turbulence, and then the order of 10 to the 4, 10 to the 5. If you do simulations, basically what we do is we assume channels which are maybe 1 centimeter, 0.5 meters per second, and the Reynolds number is 6,000. We now did also 15,000, but the order of magnitude is obviously smaller than this. The friction Reynolds number based on the friction of the wall, now is the order of maximum 400 we did, compared to something like 10,000. So there is a disparity of scale of Reynolds number here. But if you now go and analyze the particle size, we see that particle size in this application, they go from 1 microns to 1 millimeter. That means the particle size compared to this friction length scale, this viscous length, is of the order of 1 to 100. So basically the particle in what is called the viscous units are of the order between 1 and 100. And this is basically what we reproduce in our simulation. In our simulation, the particle size goes from 10 to 40 plus units. That means that what we can reproduce is the ratio between the particle size and the smallest turbulence. So these particles, compared to the smallest vortices in the flow, are of the right size compared to applications. But of course, what we don't reproduce is the ratio between the particle size and the particle diameters. That means that our particles are much bigger compared to the particle diameter, because it would be too expensive otherwise. So our particles are bigger compared to the diameter, but they are not. But they are of the right size if you compare them with the smallest vortices of the turbulence. So we match the particle size compared to the smaller vortices, but we cannot really match the particle size compared to the pipe diameter, at least for general applications. So I think, but the fact that we reproduce many of the things that's seen in experiments suggests that probably this is what is actually important. It's not the size of the particle compared to the big vortices. And this is because the big vortices are anyway strong, so the particles are kind of passive compared to big vortices. But what matters for the modulation of turbulence is how the particles interact with the small vortices. because then particles can filter the smaller vortices and then affect turbulence. Okay, so this is now an example from the largest simulation we did. The last number is 12,000, and we use 640,000 particles, which are now 10 in plus units, so they are relatively small. We have some animations. Where is it? Oh. You see now, this is a side view of the particles. These are only the particles seen in this movie, and they are colored by their velocity. So red is faster, the velocity in the center of the channel is faster compared to the one close to the wall. Here we see a view from behind. The flow is going inside the screen. You see this structure of high and low velocity close to the wall that can also be seen here in the stock view. And this is classical structure, typical structure you can find in turbulence, in single-phase turbulence, or without particles. So what we wanted to do here is to try to understand how we can model the presence of the particles in the channel. And this is a modeling we did. Basically, this is classical results from single-phase mean velocity profiles. What one can show is that what are the scaling parameters of the viscosity, the friction at the wall, tau wall, which defines the velocity scale, and then the channel size, h. So close to the wall, we assume that the velocity profile can only depend on the friction velocity and on a scale delta, which is small scale related to the viscosity. Far from the wall, instead, we have that the velocity profile will have to be function of the distance from the wall normalized with the gap, basically with the channel size. So if there must be an overlap within the region in the center of the channel, the linear wall region, this means that this y over u, du dy, which is basically the viscous force somehow, that must be a constant. It cannot depend on the distance from the wall, it cannot depend from the viscous scales. This leads to this logarithmic law for turbulent flows that is used to model basically turbulence in many CFD applications and industrial applications, because instead of resolving the wall, which is very expensive, you can assume this logarithmic wall and model the presence, this logarithmic law and model the presence of the wall. So what we want to do is we try to see if we can generalize these laws for near wall and in the case of the presence of spheres, of solid particles. Now what we observe here is that if we do simulations here with the presence of the particles, which is this red and green, and we do simulation where we assume a continuum model, so we assume that still there is one model, while there is like equation for one fluid with a modified viscosity and a modified Reynolds number, there is a big difference. So there is no similarity if you assume that you can model the presence of the particle as a single phase flow with a modified viscosity. But what if you now look at the velocity profile scaled with the effective viscosity, then you can see that, okay, it's a little bit better, but still is not a good model. And this is because the particles are relatively large compared to the smaller vortices in the flow. So since the particles are relatively large compared to the smallest vortices, like 10 times, 20 times, then we cannot really assume that the particles are completely slave to the flow. They are not only changing the viscosity of the flow, they are really changing the turbulence. So that's why this relatively simple model will not work. Oops. So what is the model based on? Basically, we assume, by looking at the particle stresses we did before, that there is a particle wall layer. This is the sketch of the stresses. So it means the particle stress is dominant only in a region close to the wall. So there is a particle wall layer where particles move attached to the wall, and more or less like a porous medium, like a moving porous bed. And then there is a region far away, relatively far away from the wall, where which behaves as an homogeneous suspension region. That means that here there is a more or less classic turbulence, but the viscosity is not the viscosity of the liquid, but it's a modified viscosity by the presence of the particles. We can estimate this particle wall layer to be proportional to the volume fraction to 1/3 and to the diameter of the particle. So this is really basically one particle diameter. This is a layer which is of the order of one particle diameter. in which you assume that there is no real flow, but there is a dissipation which is due to the presence of the particles. It's purely due to the presence of the particles. And from that region on, you have a more or less classic turbulence, but with a modified viscosity. If one combine all of these, one can write an equation for the velocity where you basically shift the origin from the wall to the end of this particle wall layer. And then you shift the stress at from the wall to the end of the particle wall layer, so that you have a modified say stress at the interface. If you do that, then one can show that you can collapse almost all the velocity profiles in one line, and the same here for the velocity far away from the wall. And there is one point that we have kept here, is these black points, but these black points are for a low Reynolds number, so in that case you cannot expect a real turbulent flow. So basically by modeling, and then we can extend this and predict the drag of the flow just by giving the flow rate. If you tell me the flow rate and the amount of particles, I can estimate the total drag, which is this friction Reynolds number, and the error is between 3 and 4%. And why that? Because we have assumed that basically the particles, in the center of the channel, they are relatively small compared to the big vortices that are there, so they are kind of slave to the vortices, so they can be considered as just relatively passive. What they do is to increase the viscosity of the fluid. Because of course the fluid with particles is more viscous, because of the presence of the solid particles. But of course this will not work alone, because close to the wall, where the vortices are smaller, then the particles are dominating the dissipation. So we have a region close to the wall, which is where the dissipation is dominated by the particles, and the region in the center where vortices and turbulent structure are bigger, where instead the particles just increase the viscosity of the fluid, basically. So everything can be rescaled in that case, but only because we have taken into account the different behavior of the wall. So all of this was good, because basically we can understand the effect of particles in two ways. At the presence of the particle wall layer, we shift, basically creates a virtual origin for the mean velocity profile, and then using an effective suspension viscosity. So we have a modified viscosity for the part in the center of the channel. And we have validated this against several simulations, and more recently also against experiments. But then, now quickly I want to mention a few more things, but more or less in detail. Of course, our work was mentioned in this focus on fluids, on the Journal of Fluid Mechanics, and then was like, okay, but what happens if you change the density of the particles, the shape of the particle, and so on. So then we started by changing the shape of the particles, and we realized that, okay, now all of a sudden it becomes quite different. So now what we did is, with the semi-inverse boundary method, we take these spheroidal particles. They can be oblate if the aspect ratio is 3, so larger than 1, basically like rugby balls, elongated particles. And then we can have oblate particles, disc-like particles, like this, like coins or discs, when the aspect ratio is less than 1. So what we do is, okay, let's put now these particles different shape in this channel, and we repeat the same simulation. Let's see if something changes, how important is the shape. Now the shape is not extreme here. Aspect ratio is 1/5 and 3, but these are not really fibers. They are still aspect ratio 3, or really like the balls for American football, for example. But this is because to make longer will be very difficult computationally, because you need to resolve the points, the peaks of the particles, the extreme points here. So this is just one movie. We see these disc-like particles, how big they are compared to the channels, and these are these oblate particles, which are like elongated particles. Okay, so what happens in this case? This is now, basically everything is summarized here. This is the aspect ratio from discs, very flat discs, to oblate. This is spheres. Aspect ratio 1 is a sphere, and this is 1 is the value of the total dissipation in the absence of particles. So that's basically the single phase flow, and 1 is the normalized with the dissipation of that case. So we see that if you take single phase flows and we add particles, we have an increase in dissipation. And that's the same you can see here. This is the volume fraction. This is the Reynolds number, which is basically the pressure drop, the dissipation. It increases when I put particles. And you see that these are different contributions we saw before. The blue is the viscous stress, or more or less always the same because Reynolds number is not changed here. The only thing we change is the particle shape, and we keep 10% volume fraction. The yellow is the contribution for the particles, and you see that, okay, contribution for the particles more or less is constant. Changes a little bit, but it's not big differences. What changes a lot is the green part, which is basically the turbulent contribution to the total dissipation. So we see that the shape has a significant effect on the turbulence production. So in the case of sphere, the case we analyzed, let's say, more in detail at the beginning, now we have an increase of the turbulence contribution, this green region. And this can be explained by the presence, also the presence of the wall layer, because particle moving close to the wall facilitates the interaction between the central region and the wall. Somehow they lift fluids up and they so that they increase turbulence production and Reynolds stresses. Now, if I take oblate particles, so these disc-like particles, they make them flatter and flatter, then I move here from 1 to 1/5, and you see the turbulence production decreases. So the gray region decreases, and so that overall I have drag reduction. The total drag goes down to less than 90%. So I have 10% reduction compared to the case without particles. Surprising, because I put 10% of rigid particles big in the flow. Instead of having increasing about 20%, I have a decrease of about 10%. If I have elongated particles, I also see a decrease of turbulence, so that overall I get back to the value without particles. So, and okay, this is now the case where I increase the volume fraction of the oblate particles. We see that I always attenuate turbulence as I increase the number of particles. Of course, this is compensated a bit by the fact that having more particles, I have also more dissipation due to the particles. So how do we explain this reduction? There is a reduction in turbulence when, in the case of disc-like particles. And one way to look at this is the stress, is to look at the particle dynamics. So this is now the local volume fraction. This is the particle, the volume fraction, so the solid phase versus the distance from the wall, where now the wall is at 0. So this magenta line is the case of spheres. You see the particle wall layer, this layer of this peak in concentration close to the wall, at a distance of about 1 particle diameter, and then goes to a constant value, about 10%. If I now look at oblate particles, and also prolate particles, then I see that if they are not spherical, the particle wall layer disappears. So this wall layers that was responsible for this increased dissipation for spheres now completely disappears once we have these oblate particles. If I now look at rotation rate, this is a rotation rate for spheres. You see it goes up close to the wall. So it means that this wall layer, this particle wall layer at the wall, particles are rotating close to the wall. They are rolling on the wall basically. And that increases mixing and increases dissipation. But oblate particles, you see how 1/5, they almost have no rotation. They just don't rotate. They kind of move close to the wall without rotating. If you look at the angle, the orientation angle, you see that the angle goes to 1. It means that they're basically parallel to the wall. So these oblate particles, they move parallel to the wall and don't get too close to the wall. So they are a little bit lifted from the wall and they move parallel to the wall. And this basically kills the turbulence because there is no particle wall layer. And by placing this layer of particles in between the wall and the center, also quenches these turbulent fluctuations. So to say, this is a movie. So now we have, basically what we have seen is that we can have very different behavior as soon as we change a little bit the shape of the particles. So the turbulence activity gets to lower values than those obtained only by considering an effective suspension viscosity. And this is because the oblate particles tend to be parallel to the wall, and stay a little bit, and they don't go too close to the wall, stay in the vicinity of the wall, and they rotate much less than spheres. So they kind of form like a moving carpet, moving parallel to the wall, and this dampens the turbulent fluctuations. Also, prolate particles have a similar effect, but now they rotate a little bit parallel to the wall because they're elongated and they can rotate around an axis which is normal to the wall. So in that case, they are not as effective as these flight-like particle-like coins. Okay, for 5 more minutes, I want to show a little bit what we're doing now, adding heat transfer. We're doing simulation of heat transfer in fluidized beds and also in pipes. So what we do is, okay, now many of these particle-laden flows are interesting for industrial application where also heat exchange is important. And for example, one motivation to start this came from Tetra Pak, is the company in Sweden. They build machine for food processing. So what is important there is that, for example, they transport food. Of course, there is a pressure loss due to the food. But what is important is that while transported inside the pipe, the food stays above a certain temperature for a certain amount of time, because that food needs then to be eaten and sold. So for sanitary reasons, it needs to be warmed up during the process, so that it's kind of possible to sell it. So then what we did is we look at heat transfer in the suspension. And what we do, basically, we add an equation for the transport of the energy transport, the temperature transport, inside the fluid and combine with the transport inside the particle. In a similar way as for the particles themselves, but now we solve the temperature equation on both phases, so that we can have different heat capacity and so on. So, and then, okay, we do the wall. So this is just one validation. This is a laminar flow where you have one hot wall, one cold wall, and then we see how the heat transfer from one wall to the other is affected by the presence of the particles. And then this is more a validation of the code. This is our numerical result. And this is this correlation found from experiments, function of the volume fraction and the Peclet number. And then we see that more or less we are able to reproduce this heat transfer, but not so well for this case where the particle Reynolds number is 16. That means that in this case where the Reynolds number is not 0, we have inertial effect, so there is enhanced heat transfer due to the inertia, which was not in the model, in the experiment, so we cannot really match. Then we looked at pipe flow now with particles of different sizes, large and small. This is really done in collaboration with the experiments and the industrial partner there. So, and then what we do, we look at heat transfer. In this case, we have the wall which are hot, and the heat is transferred inside. And we want to make sure that the particle center reaches a certain temperature, let's say stays above a certain temperature during the transport. And we see how the heat is transferred from the wall into the channel, into the pipe. So if we look now at the case of a laminar flow, so in this case low Reynolds number, we see that this is the effective heat transfer. So this is the ratio between the heat transfer with particles and a pure fluid. We see that if we increase the volume fraction of particles, we have an effective increase of the heat transfer. And this is done for different particle sizes. These are big particles. Many big particles help heat transfer more than fewer smaller particles. But we see that while there is a significant effect in heat transfer, so I can really have 2.5, 3 times more heat transfer with particles. If I look at the pressure drop, so the dissipation in the flow, this is almost independent of particle size. So the particle size in this laminar regime don't affect the dissipation in the flow, but what they do is enhance much more the heat transfer. Then we look at turbulent flows. Of course, turbulent flow now again, there are spheres, now we have an increase in dissipation in the flow. And this is an integrated heat transfer. Basically, it's a non-dimensional measure of the mean temperature inside the pipe. And what we see is something initially surprising, that this is the case without particles. So this is time, as we start to warm from the walls. Initially, the temperature is lower in the case without particles, and then it gets above the case with 30 and 40% volume fraction. So the heat transfer is initially more efficient in the presence of particles, but then becomes more efficient when you have few particles, like only 5%. So this I want to explain why, and this is explained by the fact that in the case with many particles, you have a strong reduction in the fluctuation. These are the velocity fluctuation. This is the pipe radius. This is the wall. This is the core. And we see that when we add many particles, 30, 40% volume fraction, and we basically kill all fluctuations in the center. So now we are back to that regime we saw before, where the transport or the dissipation is dominated by particles. In that regime dominated by particles, the fluctuations are small. There is no correlation between the velocity fluctuations. That means that now heat transfer becomes less effective. And this maybe can be seen better by this movie, where we see that, okay, in the case with few particles, initially the heat transfer is slow, here is faster, it got warmer here, it's more yellow. But then for longer times, the heat never really managed to come inside here in the core. So you see the core is warmer here than here. Because here when you have 40% particle volume fraction. There's many particles, so it's not really a turbulent flow with strong fluctuations, and so the heat cannot really penetrate easily inside. So we have, since we have strong dissipation because of particle stresses, but we have basically no Reynolds stresses, no fluctuations because of these many particles, then we see that heat transfer is slow here in the center. It's more efficient if you have less particles. Okay, now I finished. This is something we are doing now with fluidized beds. Basically, we have hot particle in a cold fluid. They are blown inside, and then we see how they cool and they exchange heat with the flow as they move upwards. Okay, maybe I can close a little with this. Where this is something we started this summer. Now we look always at this particle. Now this particle represents droplets, evaporating droplets. This is again the channel. These are the evaporating droplets that are injected like a spray. And then these are some of the parameters of the simulations. And we see here the thermal waves and the heat around the temperature around each of the particles. And this particle evaporates. So from a technical point of view, what we have is that the particle changes size. So these Lagrangian points also have to change during the simulation because the particles shrink. So that adds some additional complexity. And then also what we did now, we need more complicated boundary condition because we need to impose continuity of we have mass and heat transfer at the interface. So we need basically fluxes of heat and mass at the boundary here of the droplet. And so to do this now, we cannot only use one set of Lagrangian points, but use a second set of Lagrangian points, which extend into the gas phase, so that we can get here some estimates of the derivatives, for example, the heat flux, the derivative of the temperature, or the derivative of the concentration, that then we use to estimate the evaporation rate. What we assume is that since these are small droplets, and the temperature inside is uniform. Since they are small, there are large heat fluxes, it's very fast to reach uniform temperature inside the particle. Okay, I think that's it. Thank you.